And today our speaker is Vitalii Konarovskyi with the talk about modified flows, mean field limits, and stochastic gradient descent. Please, Vitalii.
Hey, thank you so much for the opportunity to give a talk, and also thank you for the introduction. It is a great pleasure for me. My talk is based on the joint work with Benjamin Guess and Sebastian Kassing from Bielefeld University. And the aim today is to talk about the applications of the stochastic differential equations, which interactions which first appeared in works of Professor Dorogovtsev and Professor Kotelenets, and then were actively studied here in the Department of Random Processes. We will discuss how this type of equations can be used for the approximation of the stochastic gradient descent dynamics in the machine learning. We recall how the main goal. We recall that the main goal of the supervised machine learning is to clarify data according to some their specific properties. Usually, one works with labeled data set. In this case, one needs to construct an algorithm or a function which would map a future data into its label. The construction of such an algorithm or a function is based on a large available training data set. Therefore, we assume that this is that training data set. Can you see my cursor, what I show?
Yes.
Okay, good. Thank you. It is a training data set with data theta I and label gamma I. It is also natural to assume that theta I are sampled independently from an unknown distribution, which we will denote by P, and gamma I is the image of the corresponding data under a function f that has to be modeled. In the supervised learning, to model the function f, one can use a parameterized family of functions u, where z is a parameter which has to be found. For instance, if data are vectors, it can so the function u can be, so for instance, it can have such a form or be the iteration of functions of such a form where h is a fixed function and CAB are unknown parameters, which play a role of matrix or vectors and so on. In this case, one talks about the approximation by a neural network. To measure how good the network to the true function f is, one can fix a loss function L, which measures the distance between values of both functions, and then define the generalization error as the expectation of the loss function with respect to the distribution P. And now, having the mathematical model, one needs to find a parameter z which would minimize the generalization error. So for this, let's denote by r tilde the loss function of the value of the true function and the network. And then the generalization error is the expectation of r tilde with respect to the distribution of theta. Usually, stochastic gradient descent algorithms are the most common way to minimize the generalization error in machine learning. So taking any starting parameter z, we defined the dynamics by updating the parameter in the direction minus the gradient of the function r tilde, computed and on a randomly chosen training initial data. then one can prove that if the generalization error R satisfies some good properties, for instance, it is strictly convex, then the dynamics Z will converge to the minimizer of the error function R. However, many computational experiments show that that even if R is bad function, for instance, it is associated with a network with a large number of parameters, this approach still works quite well. And therefore,
excuse me. You claim that, for example, if the cost function is non-concave, so it has several local minima. What happened? It still get a global minima, or just?
I claim the following here: that, for instance, if you take big data set of pictures, then after that you will build a network. You will learn it, and so on. And in network, there will be a really huge number of parameters. So still roughly speaking, the limit of the stochastic gradient descent will give you some expectable result. Actually, you will see that network actually will give you the approximation of the true function. So I claim only that. Here is no mathematical claim, because at the moment it is not clear.
Exactly my point. So there are a lot of examples of complicated situations when this method works well.
Right. It is exactly that I wanted to say. Thank you, Adrian. So and therefore now so this phenomena is one of the important. I want to say that the most important problem in machine learning is to understand this phenomena. So, and to understand this phenomena, it is important to understand the dynamics of the stochastic gradient descent. And one of the way to analyze the stochastic gradient descent is to consider its continuous limit when the learning parameter gamma is small. So the stochastic
What is eta, do you mean?
this eta, so here.
Yes,
Eta,
yes.
I'm sorry. In this case, the stochastic gradient descent dynamics can be described by a stochastic differential equation driven by a Brownian motion. So let me quickly just recall that. Let's rewrite the stochastic gradient descent as follows. We add and subtract the expectation of R tilde and denote this expectation just by R. So R, it is the expectation of R tilde, and this difference, so gradient of R minus R tilde, denoted by G. Then we see that it is the Euler scheme for the following stochastic differential equation, where sigma is the covariance of the function G.
Excuse me again. You maybe will insist that this green summan green difference has zero expectation.
Right. It has a zero expectation.
But why it is so? Because we just take a gradient of the function R, and then we take gradient of the expectation. So we must have some good conditions when we can interchange expectation and gradient.
I mean, here, let's assume that everything is smoothly bounded and so on.
Okay, good.
Let's not focus on the technicalities, since this is not the main point of my talk. I would like to give some motivation, and after that we will go to some rigorous result where also I will mention the conditions, and then we can discuss, all technical details, okay? So here I only want to say that now we get that we replace the stochastic gradient descent dynamics by a solution to this equation where sigma is the covariance of the function g. And the advantage of this approach is that now the dynamics is driven by a Gaussian noise that can simply be understanding. So then the stochastic gradient descent dynamics, which is actually driven by the noise generated by theta. So recently, in the Journal of Machine Learning Research, Litai and Wine and Eo proved that if R and the square root of sigma are smooth enough, then this stochastic differential equation gives the approximation of the stochastic gradient descent dynamics on nice functions f up to the first order atom. And moreover, it doesn't matter if the diffusion term is presented in the equation or not. Even if we assume that we have the diffusion term here, still we will have the order atom.
So it looks like we discuss the Euler scheme and we discuss the speed of or distance of approximation to Euler scheme in metric of weak convergence. So there are a lot of such results well known probably from the 70s or 80s.
Sure. But it is not my point. I didn't finish my sentence. I want to say that what is done due to Litai and Wine and Eo, it is an observation that if we consider this metric and we introduce some correction term into the drift, we will get the higher order approximation. We will get the approximation to the eta square. So, and he also considered different models which appears in machine learning and so on, different equations, for instance, equation with inertia and so on. And so it is a particular result on which I would like to focus because I will talk something similar, but in infinite dimensional spaces. Okay, so
I'm sorry, I don't have a question, but if you add this term, it no longer is the standard result for the Euler scheme, right?
Yes, right. Okay, good. I want to say also that we will discuss this phenomena why adding the correction to the drift term leads to higher order approximation later, discussing the result. So our results.
I think that there is a book of Kuznetsov, very large, about the difference approximation for stochastic differential equation, and there are not only first order scheme, but second order and so on. He discussed the possibility of making difference approximation much more faster than.
Sure. I'm sure that such result exists, and also I'm familiar with some kind of result. Here, the important thing is that the equation is not the main object, and we don't do the discrete approximation of the equation. We have some discrete dynamics, and then we want to get the approximation by a continuous object. And here you have much less freedom than you have when you do the approximation of solution to the stochastic differential equation. Also, let me tell about that a little bit later.
Okay.
You will see. Okay. Now I just want to say that this equation now is actively used in machine learning research for the study of the stochastic gradient descent dynamics. But this equation has a few disadvantages. So first of all, the matrix sigma is not necessarily elliptic. So therefore, one should not expect that its square root has enough regularity, even if R tilde is smooth enough. So for instance, if sigma is equal to y squared, then the square root is absolute value of y that has a limited regularity. But in this result, the regularity of square root was important. Secondly, the equation doesn't catch the endpoint motion that is important for the dynamical system approach that aim on the use, for instance, the stability where one needs to consider endpoint motion. And and if we denote by that of that the stochastic gradient descent dynamics started from that, then one can easily see then this equation doesn't give the right approximation of the HGD dynamic when we consider a few motions simultaneously. And roughly speaking, here the reason is that two vectors have different covariance.
Mm-hmm.
So therefore, the first result which I want to present here is that there is a way how one can overcome those difficulties. For this, we need to change the noise which drives the equation. So let's recall how the HGD dynamic is defined here. And our idea is to replace the diffusion term here, which consists of the covariance G, by the term where where we have the integral with respect to a cylindrical Wiener process, defined on L2 space of functions on training data. So, by the way, I would like to know that the martingale problem for both equations, this equation and that equation, are the same. But what is nice that now this equation, first of all, it catches endpoint motion, and also it doesn't require the regularity of the square root of covariance. So in particular, we come to the following result. If the function r is r tilde is regular enough, then for every smooth bounded function f, the endpoint motion of the stochastic gradient descent dynamics is approximated by the endpoint motion of this equation up to the order eta square. And moreover, the image of any probability measure under the stochastic gradient descent dynamics can be approximated by the image of this measure under the flow x, also up to the same order, up to the second order. And let's remark, the reason, I want to say that we will talk about the proof of this statement later when we will discuss more general result from which this statement will follow. So do you have any questions here about the formulation of the statement? Okay, if no, then now I would like to make one step back and talk about the application of our idea to the over-parameterized stochastic gradient descent. So let's come back to the first slide and recall that we approximate the true function f by parameterized family of functions u. But it can happen that the function u is far away from any function of this class, or we want to improve the approximation of function f. So then one of the way is to increase, for instance, a number of neurons that is the dimension of the parameter z that is equal to d, and consider a larger network. But this can be very computationally expensive. So therefore, here another way could be to fix the network, probably with not a large, very large number of neurons, and then take the average over many parameters. So do like that. So approximate the function f by the average of the function u at different parameters zk. Oh, let's remark that this sum here can be written as the integral of function u with respect to the empirical distribution of parameters zk. This regime is
I'm sorry, I have a question about the formulation. Once I listened to some talks where people were speaking about a parameterized regime as a regime with a large number of parameters. They actually were speaking about maximum extremal manifolds. So you don't have minimal points, you have manifolds because there are too many parameters. The space of parameters is too large. But here you're doing something slightly different, right?
No, so the question with manifolds also is not so trivial, because actually always you need to choose how you parameterize your family. I mean, still to talk about some manifolds and so on, probably you can talk about manifolds of the parameters. Maybe you are talking about that. And still in this case, it is not clear. I mean, here is a many way of parameterization, and then many way of underlying topology there. You can consider either Wasserstein topology, you can consider Euclidean topology, and so on and so forth. Now, I don't touch this question here. I just say that I want to work with a huge number of parameters. I don't refer to the to any kind of geometry on the set of parameters. But I consider a special way of approximation. Instead of one network, I consider the average of network under large number of parameters.
So you train a number of networks and then average.
Right. But I train them simultaneously. So I consider, and you will see now in a few minutes, when we will talk about the stochastic gradient descent dynamics, that all coefficients are. I mean, you cannot independently train every parameter and then take average. On every step, you need to train all parameters simultaneously. And actually, this creates a lot of problems, a lot of computational problems, because the number of parameters could be.
Oh, now I see why it's over-parameterized. Thank you very much for the explanation.
Over-parameterized here because actually the number of parameters could be larger than the number of data in training.
Yes, when M is large. So, thank you very much.
Okay, and also in this case, we will work with square loss function. So then the generalization error has this form. It is oh, I'm sorry, here L should be deleted. It is just the absolute value of difference of two functions to the square. By the way, this model was discussed on my previous talk here, where we considering the description of CLT fluctuations of the HGD dynamics in the overparameterized regime. So now let's talk about the stochastic gradient descent for this case, starting from some initialization which are independently distributed from some fixed probability distribution mu0. So every parameter zk can be modeled using such a stochastic gradient descent, where we update every parameter in the negative direction of the gradient of the loss function multiplied by the learning rate. So now using the form of the approximation function fn, one can see that the gradient part here can be rewritten as some function v, which we denote by v tilde, that depends on the parameter itself and the empirical distribution of the parameters. Next, similarly as before, we can see that it is an Euler scheme, roughly speaking, for the following system of equations, where mu m is an empirical distribution for solutions x. Oops, I'm sorry. And here V is the expectation of V tilde, and G is the difference between V tilde and V. By the way, the martingale problem for the empirical distribution mu m for large M was derived, for instance, in the work of Roscoe and Weidenheiden in the Communications of Pure and Applied Mathematics. However, a rigorous investigation of that martingale problem, in particular the well-posedness and its connection with the AGD dynamics, were missed there. And the rigorous results regarding those questions were obtained in our recent work with Benjamin Guess, Richard Gbalani, and myself. In particular, in that work, we have shown that the mean field limit of the AGD dynamics when the number of m goes to infinity. So the mean field limit and also the fluctuations of this mean field limit can be described by this stochastic differential equation with interaction whose coefficients depends on solutions itself, and also the measure mu, which is obtained just by transporting the initial distribution or initial measure mu0 under the flow x. So this equation, by the way, this equation is now well studied, for instance, by Andrei Drogovtsev, Petr Kotelenets, Andrei Pilipenko, Lena Ostapenko, and also many others. Today, I want to show that including some additional terms into this equation, where D denotes Lyon's derivative, what it is I will tell a little bit later, leads to the higher order approximation. So namely, if we include this term and also make a good assumptions on the coefficients or on the function u in the network approximation, then this equation gives the second order approximation of the AGD dynamics in the overparameterized regime. So actually, we have a similar result in the previous as in the previous case. And also, this result will follow from more general statement, which I would like to discuss now. So therefore, if you have any questions to this result, to previous, we can discuss them. And after that, I will go to the general result, and then we will talk about idea of proof of the general result. Okay, if no questions, then let me quickly recall the definition of Lyon's derivative. We say that a function f from the space of probability measures Rd with the second moment to the space Rk is L differentiable at mu if there exists an element which we denote by df in L2 space of functions from Rd to Rk times Rd, where the inner product on that space is generated by mu, such that the increment of the function f in a direction h has this linear part. So here these brackets denote the inner product with respect to mu. If you are more familiar with functional derivatives, then for a nice functions f, the notion of L derivative coincides with the derivative of functional derivative. for instance, if f is a cylindrical function, then Lyon's derivative, it is just the derivative of g, and then the gradient of function phi. So the functional derivative is without this gradient. And then the Lyon's derivative, it is the gradient of the functional derivative in this case. Okay. Also, we will also say that f belongs to the class CB1 if f is every differentiable at every point mu, and its derivative has mu version, which is jointly continuous with respect to mu and x, and also bounded. And similarly, we can define the class of M times differentiable functions.
So it looks like this definition is built for example for the functions which are multiple integral with smooth kernels with respect to measures from
maybe.
Okay.
Okay, now fix measurable functions v and g, and also assume.
By the way, Vitaly, can I just ask you again? Can we back to this slide with definition of Lorentz derivative? And let me ask you if the measure mu has density, then nothing changes, nothing happens. Yeah, we cannot move this derivative to the density to get something like derivative of density. No. Yeah.
If you want to talk about the functions of densities,
Yeah.
then I'm not sure, because is that actually even continuous operation?
Yeah. So it was just my question. Yeah.
No, I'm not sure that here should be something probably reasonable.
Yes, because from other point of view, for measurable processes, it is sometimes natural to use Dawson derivative when we just try to slightly move initial mu with the delta function in some point and so on. So it is different.
Here for us, it is better to work because, first of all, generator can be written nicely, and also there are some properties which already for this type of derivatives which we can use and so on. But I remember when we started to work on that questions, we started from functional derivatives, and later we understood that this type of derivatives would be more convenient for us. At least functional derivative where you do increments in delta. If you do that directly, you need to go outside the space of probability measures.
Exactly. Yes, you go outside. But by the way, for function from your example, you will get the right answer. You will get this gradient of phi too, because you move.
Okay.
Okay.
Okay, let's go further. We fix two functions, and as before, we assume that expectation of g is equal to 0. And now we define a Markov chain nu, but I will numerate this Markov chain by points Tn, just to have like the same scalings and so on. So here Tn, it is n multiplied by eta. So we defined the process nu as the image of the initial measure under the similar transformation as we had before when we discussed the overparameterized case. And we also consider a solution to the distribution-dependent stochastic modified flow. So here, with these corrections which we have here, then our result reads as follows. If we assume enough regularity for functions v and g, and by the way, here we didn't try to be optimal. So having this regularity, we claim that for every also smooth function phi, you have also the approximation to the second cone.
Constant is dependent on phi, yes, and on the coefficients of constant.
Right, of course, and derivatives of phi. And also here, you see that I wrote here for every theta, let's assume that this bounds, the constant which bound all derivatives of g is independent of theta. We have a little bit better, we have better result in the paper, but I don't want to include here many conditions. I want to show you just some true result and also show you the idea. If you want to find more general result when these coefficients, I mean, have a little bit more general structure, then you need just to go to our paper and then you will see that. So here, let's assume that also G is uniformly bounded. Okay, now let's talk about the main idea of proof of this result. And we denote, for this, we denote the transition semigroup associated with the HGD dynamics by S. It is defined here. And the semigroup associated with the measure-valued process mu t is denoted by tt. Then the difference of the expectations of phi at values of processes, of both processes as time tn, or say mu and mu, it is actually the action of the operator Sn on the function phi minus t at Tn of function phi. And then we add and subtract the intermediate terms there. So here. And also now we have, and now we put outside the brackets of the operator S to the power n minus I minus 1. So in brackets, we have this one. So here is clear that we have this one. Also, we have t at the point ti, but using Markov property, we have t of t. And you see here and here is the same function. Let's denote it by some function u, which depends on ti and also mu0. So therefore, you see that actually we got the sum of operator S to some power, which acts on the difference of S and t at eta on some function u. And also, let's observe that this S, it is actually comes from the expectation. Therefore, when you estimate the supremum over of mu of S, it can be just estimated by supremum of the function psi. So therefore, we can estimate the absolute value of this difference and then supremum just by the sum of the supremum of differences just for one step in the both processes. So just one step for that for the chain and also minus t at point eta of u. And now the idea is to get the estimate for these terms here for one step get one step estimates, and for this we want to get the expansion of S and T with respect to the powers of eta. And we will start from the expansion of S in the series, in the power series of eta. So for this, let's fix theta, and let's consider one-step transformation z eta as a random variable in this parameter z in this probability space. So. And also, let's define this random variable psi of S, which also we consider this for fixed theta as a random variable in this probability space. Okay. And then the image of the measure mu0 under the map, this map Z, is just the law of psi at point 1, or just the law of this process Z. When you take S is equal to 1, you have just Z, and nu eta, it is just the distribution of psi 1. And then we can use the Taylor formula. So because now you see that parameter S is just a real number, function also takes the values in the set of real numbers. Therefore, we have just a usual function. We can at least formally write the Taylor expansion with respect to S, and we get this equality. And after that, we need to compute every derivative in this expansion. And in order to compute the derivative, let me just formulate the result, which can be found, for instance, in the work of Ren and Feng Yu Wang. This statement says the following. So if we have a family of square integrable random variables on Rk defined on a probability space, and also we know that this process is differentiable at 0 in L2 sense, so it means that this limit exists, then for every smooth function f, one has that the derivative of f at 0 is given by this expression. So therefore, we want to use this formula in order to compute the derivatives which we saw in the Taylor formula. And let me recall that our process Z now is linear with respect to Z. So therefore, the derivative of psi, it is just, say, usual derivative when you fix everything. And you have this thing, and it is equal to eta multiplied by the function v plus function g. So therefore, in particular, the derivative of psi with respect to S, for S is equal to 0, it is just, according to the formula above, it is just the expectation of the derivative f computed at the distribution of psi, comma psi, and then scalar inner product with the derivative of psi. And now let's remark that psi 0, when you take S is equal to 0, it is what? It is just Z. And you are on the probability space with the reference measure mu0. So therefore, the distribution of Z on that probability space is mu0. It is Z, and actually you get this term. You can do the same trick for the second derivative and so on. And then you will come to the expansion that S of psi is equal to the function psi at mu0, then some term multiplied by eta, then some another term multiplied by eta square, where you can everything precisely compute it. And you have the rest term where the rest term, the supremum of rest term, can be estimated by the norm, by the supremum norm of derivatives of the function psi. So, okay, we have this expansion, and then our idea is to also get the expansion for the semigroup T eta. So for this, let me recall that we have this equation. Then I'm sorry, here should be T. T eta of psi is equal to psi plus integral of eta, the generator associated with this equation on Ts of psi ds, where this generator can be, so has the following form. It is some differential operator plus eta, another differential operator. And for instance, when so this one, it is written, it has this form, but that term which comes actually from this term, I mean, this operator which comes from that term, and also this term also has some form. I didn't want to put it on slide because I didn't want you just to go through terms and so on. Now it is not so important for us. For us, I think it is important an idea of what we do here. And now having this equality, we can iterate that equality. We can put this I'm sorry, here again, and do one iteration, and therefore you can see something like that. So you can see that it is eta L1, which acts on psi, and then eta square L2 plus 1 over 2 L1 to the square, also which acts on psi. And then you will see some rest there. And now the role of these correction terms here, which which we included here, is exactly that the term here and the term here are the same. They will cancel each other when you consider difference. So without that term, so if you don't have this term, so you will not see that cancellation. So therefore your difference will be up to eta square. But if this term and the term on the next slide are the same, then you will have the difference is up to the order eta to the power 3. It also explains the reason why talking about just one order approximation, I mean, why also it doesn't matter whether you include the noise term or not, when you talk only about the first order approximation. Because when you don't include noise, but you only see the drift term, so then you will, for sure, you will have that this term is the same. And these terms will be different. So therefore, you will have only the difference will be up to the eta square. So, and let me then after this remark, let me continue that then this supremum, it is less or equal than the sum of supremums, as we said. And then you see, since the terms which consist of eta and eta square are cancelled, you have eta to the power 3 and the difference of rest terms, which can be estimated by the supremum norm of the derivatives of this function u. And so therefore you have eta to the power 3 multiplied by n, because you have n terms here. But you see that we consider only times tn, which are less or equal than t. So therefore, this n together with one eta can be replaced by t, and you have the second order approximation. And everything what we need to care about now, it is only about the good regularity of this function u, which we have here, on which we estimate two operators. Let me probably go back and recall you that this function u, it is actually the semigroup which is associated with solutions to the stochastic differential equation with interaction. So we need to say something about the regularity of this semigroup. And here I would like to refer to the work of Feng Yu Wang. It is a recent work who studies the semigroup generally associated with solutions to the equation with interaction. He calls this equation image-dependent stochastic differential equation. And his result, or in particularly his result is the following. If you assume good regularity for coefficients, then the associated Kolmogorov equation has a unique solution, and also this solution is regular enough, which actually is needed for our estimate. Do you have any questions here?
So he proved that regularity happens exactly in your sense, yeah?
Yes, yes. Mm-hmm. Okay. I'm sorry. Here t should be deleted. He considered also the case when coefficient depends on t, but here we need only the result when coefficients are independent of time. And now I see I have just a few minutes. I would like very quickly to come back to these two first results which I formulated at the beginning. One case, it is just the usual stochastic gradient descent, and another stochastic gradient descent in the overparameterized regime. So it was the first statement. You saw this slide. I just put here just to recall it. And just let me tell you a few words how we can get this estimate for the particular case, say for this equation where the coefficients do not depend on mu. The second inequality, it is just a direct consequence. And only the question is how we can compare that endpoint motion. When m is equal to 1, so when you have only 1 point motion, then it is not a problem, because you can say, oh, okay, let's take the measure mu, initial measure mu, it is just a delta measure, and then the push forward of the delta measure gives you exactly 1 point motion. But when you want to talk about endpoint motion, it is not enough to take just empirical measure, which sits at that point which you want to consider, because the empirical measure doesn't record the order between processes, right? You cannot go from the empirical measure just to endpoint motion for free. So therefore, here our idea was the following. So it is my first remark that for m is equal to 1, it is just you take the measure mu, which is a delta measure, and then you get the result you will get this result which follows from general result. But if you want to show that statement for endpoint motion, then you need to do the following trick. You need to take the function now r, which depends on of z, where now z it is just this family of points from which you can consider your endpoint motion for HGD dynamics. And you consider the sum of these functions, r tilde, and then let z and x are the processes which are defined via this extended function r, like say like that. Then let's observe that if we compute the gradient of the function r tilde, then it is just a vector of gradients of r. So therefore, immediately we get that the process which comes from the stochastic gradient descent dynamics for r tilde x, it is just a vector or endpoint motion for the original HGD dynamics. Then let's go further. If we do the same for the expectation of r, also it is a vector. And if you do that for the correction term, also you will get the vector of correction terms. And also what is nice here, that if you take also for g, consider g extended, also it is a vector of g. So therefore, immediately you get that this process x, it's the same as, or it is exactly the endpoint motion for the solution to this equation. And then we can use this result for m is equal to 1. So let me also remark that this trick does not work when you work this equation where here is the covariance of the function g. I mean, with the equation which appears or which appeared in machine learning literature, for instance, U2, Wine, and O, and so on, the equation which I mentioned at the beginning of my talk. So this trick doesn't work. So therefore, also it is one of the reasons probably why that classical equation doesn't catch endpoint motion for the HGD dynamics. And just almost the last slide, what about the overparameterized regime? Because in the overparameterized regime, you see that the HGD dynamics starts from empirical distribution, and the continuous dynamics it just starts from the distribution mu0, where this the initial the initialization for the HGD are just m identically distributed random variables from the distribution mu0. So the starting point for mu and mu are different, but as you remember, our general result is formulated for the same initial condition. So therefore, here the idea is just to use the Lipschitz continuity of solutions to the stochastic differential equation with this interaction with respect to initial data. So let's take mu m be a solution to that distribution dependent stochastic modified flow started from the empirical distribution. Then we compare the original process, so mu, so this process mu here, with that process here. Then we can add and subtract the process which is a solution to this equation, but with initial condition, which is an empirical distribution, and use the triangle inequality. Therefore, this result immediately comes from the general result. But this term, it can be controlled by or estimated by the Wasserstein distance between two solutions of that distribution dependent stochastic modified flow, but started from different initial conditions. And then we can, using the Jensen inequality, we can go just to the expectation of square, for which we know the Lipschitz continuity. We know that this expectation is of the distance of two solutions is less or equal than some constant, the expectation of the Wasserstein distance of two initial distributions. It is, for instance, due to the work of Andrei Drogovtsev, or also we discussed this in our previous paper with Guess, Balani, and Balani. So therefore, the question is only here that to control this expectation, but then we can for the empirical distributions, and we can get that for m large enough, this term also is less or equal than eta square. So therefore, this difference is less or equal than eta square. Okay, this is two works. My talk is based on this work. The second work is devoted to the study of fluctuations of the HGD dynamics for the fluctuations of the HGD dynamics, where we also use these equations with interaction for the description of that fluctuations. Okay, thank you so much for your attention.
Thank you very much. Maybe somebody have questions or comments, please. I have several comments. Firstly, when you do this estimation between action of two semigroups, it is, I think it is very important to look for the works of Smolyanov and Jana Kinderknecht. By the way, she gave a talk maybe a year and a half ago at our seminar. Unfortunately, this week, she said to me that this week she is absent out of science, but definitely you can contact her personally, and it will be a very fruitful discussion, because the idea using this Chernow approximation was to get much more fast approximations than just one or diameter of partition. Yeah. They use uniform partition, but nevertheless. This one is the second is that when you use this distance between empirical distribution and the measure and the pure distribution, like in the last slides, I think it will be very useful to look for the work of Kolchinsky. Kolchinsky, I think from Kansas University. He did a lot on this, and I think that you can use some estimation in different distances and so on. So it will be just useful to do this. And
thank you so much. I will take a look.
And in my opinion, this is just application of the general trick, and you can do this trick don't using these words stochastic descent method, data learning, and so on. So,
of course, but I thought that in particular, I mean, for the community and also for the seminar here, it would be also interesting to see the applications, because I mean, now equations, the equations with interactions so we study actively and so on. And I think that it is always good to have some additional and important applications.
But you see, what can be interesting application? There is one case of equation with interaction where the coefficients are irregular, and this case is very famous for centuries. It is vortex dynamics. Yeah, it is vortex dynamics. It came from Helmholtz approximation to Euler equation. And here the coefficients are like gradient of logarithm, so they have 1 over norm of the difference in. But it will be very interesting to look at this case. Maybe you can use this trick to approximate such dynamics. Yeah, it will be interesting. Yeah. So let's look for unbounded coefficients too. Okay, maybe some other questions, please.
I have a question that is related to what you just said about these irregular coefficients. So if coefficient, you know that if SD, stochastic differential equation, has Holder continuous, but not least continuous, then the Euler scheme is still convergent, and we have the direct expression with convergence. This should work here more possibly.
No, maybe yes. I still am sure that Kuznetsov book is very good to see for this talk, because he studied different regions too. So as I said, this talk is just part of the general picture, and in this general picture, maybe we can derive this correction term to the Euler scheme with for equation with in the general equation for interaction with rather bad coefficients. Yes, you are right.
Yeah, because every corrections of this type that I saw, they were very ad hoc, so they have a very specific function, and they introduced the correction.
Even I think that Krylov recently did for one-dimensional diffusions with very bad drift. He did also some corrections. So it must work.
Yeah, actually the idea of correction is that you compare continuous dynamics with discrete dynamics, and actually this correction is like the price which we need to pay for that.
Yeah, exactly. Okay, so maybe some other questions or comments, please. Okay, if there are no any questions, then for today we finish our work. Next speaker will be me with
Yes.
properties of random nodes. And see you next week. Bye.
Bye. Bye.
Goodbye.